Hi, this video is on the conservation of energy. I'm going to start off by defining a couple of terms and then showing where our main equation comes from, and then using that equation to solve a couple of problems. To discuss conservation of energy, we first need to explore the idea of a system. A system is a collection of objects, and every collection of objects has some amount of energy within it. We're going to divide that energy into three categories. This kind of looks like a baseball. It's a nice way to think about the three categories of energy in a collection of objects. Some of that energy is in a stored form. We call that potential energy, and we use the letter U for potential. That might be gravitational potential energy, elastic potential energy, such as the energy stored in a spring, or maybe electric potential energy, which we're not going to work with now. Actually, today we'll only focus on gravitational potential energy. K is for kinetic energy, the energy of motion, and E therm is for thermal energy, energy associated with an object's temperature. If you study physics a bit further, you find that thermal energy is actually a form of kinetic energy down at the molecular level. We're not going to worry about that now. We'll treat it as a separate category. For example, a baseball flying through the air has potential energy because it has some height above the ground. That's gravitational potential. It has kinetic energy because it's moving. And yes, in theory, it does have, or in practice, it does have some thermal energy, but we are only going to focus on changes to the thermal energy. And so if the thermal energy of an object does not change, then it's going to be of no concern to us. If it does change, we need to know how much it changes. So maybe I should put a delta in front of the E. Change in thermal energy. But don't let that confuse you. Energy falls within these three categories. Within a system, energy can transfer between different categories. For example, it can go from potential to kinetic, or kinetic back to potential. The mechanism for transferring energy between categories is work. Work, in the physics sense, is a transfer of energy. So work can take energy from that category to that category, or vice versa. It takes a force to do work, a force and a displacement. Here's a list of forces. These three forces are called conservative forces: gravity, elastic, and electric, because they conserve what we call mechanical energy, which is the total of potential plus kinetic. That is, whenever these forces act, it only leads to transfers between these two categories, back or forth. Non-conservative forces take energy out of these categories, or put energy into these categories, thereby not conserving mechanical energy. Friction is a non-conservative force that can take kinetic energy and convert it into thermal energy. I'm going to label this arrow as W in C to show that there was work by a non-conservative force. And likewise, I'll label these two arrows as WC to show that each of these represents work done by a conservative force. So far, these four forces which we've talked about all pertain to transfers of energy within the system. However, energy can be added to a system and taken out of a system. For example, if the system is just the baseball and the earth, a person can pick up the baseball and throw it, thereby giving it kinetic energy. And that energy comes from outside of the system as we have defined it. The forces that we're going to focus on that can lead to that kind of addition or subtraction of energy from the system are tension and applied. So a person throwing a baseball would be applying a force, that would be an applied force, that added energy to the whole system. We would really need to represent that with a larger circle. Okay? The whole amount of energy in the system would change. We could represent that with a larger circle. So work done by an external non-conservative force comes from the outside and really could go into any of these categories. But I'm just going to draw it going right here. And likewise, work can transfer energy from the system out of the system. For example, a person catching a baseball takes away its energy of motion. This would be an example of positive work, putting energy into a system. This would be an example of negative work, taking energy out of a system. This statement expresses conservation of energy. All energy is accounted for. If there is no external work done, that means the system is isolated, and that means the change in kinetic plus the change in potential plus the change in thermal equals 0. That means any change in K has to be offset in one of these other categories. Again, if the system is isolated, these categories, these three types of energy, they can fluctuate, but there's always offsetting amounts. If K goes up 10, U goes down 10. If K goes down 3, E goes up 3, for example. Okay, all the changes sum to 0. If energy is added to the system, for example, 5 joules of energy is added to the system by an external force doing work, then the sum of these three changes adds up to that 5 joules of energy. The change in a variable equals the final value minus the initial value. And so we can write delta K as K final minus K initial. Likewise, we can write change in potential as U final minus U initial. We're going to represent change in thermal energy as minus work done by a non-conservative force, mainly friction. It's minus because the sign is going to be different. If friction does negative 100 joules of work, then the thermal energy goes up, increases 100 joules. So minus a negative 100 gives us a positive 100. And then again we have equals WEXT. By the way, I'm going to scratch out that delta symbol because that bothers me. I don't think that should be there actually. But it is right here. Okay, we can rearrange this equation to get yes, we can get this equation right here. And this is our master equation, and we will use this equation to solve every problem. This is always the starting place for a conservation of energy problem, at least for us. Initial, kinetic initial plus potential initial plus work done by a non-conservative force plus work done by an external force equals the final kinetic plus the final potential. This is our starting place. So let's solve a problem using this master equation. We have a skier traveling 15 meters per second, reaches the foot of a steady upward 20-degree incline and glides 18 meters up along this slope before coming to rest. What was the average coefficient of friction? When you get a problem like this, it helps to write out all the numbers provided in the problem and assign them to variables. So I'm going to start by saying my initial velocity is 15 meters per second. My initial height is going to be the foot of the hill, 0. My final speed, rest. My final height, well, it's not 18. Here's the slope. Okay? This hypotenuse right here, this is 18. D equals 18 meters. Okay? And this angle right here is 17 degrees. So our angle is 17 degrees. D, the distance up the hill, is, oh, I'm using the wrong numbers. That's 20 degrees. Sorry. 20 degrees, and this is 18 meters. Okay. Now, we start here at height 0. We end up here at a height of, well, we can use some trigonometry to calculate that height. It's going to be d times the sine of that angle. So my final height is going to be, and yes, I could calculate a number, but right now I want to represent it in terms of these variables, because my preference and what I recommend is not plugging in numbers until the very last step. Leave everything as variables until the last step. So I'm going to say d sine of my angle. Okay. Are there any external forces doing work? Any tension, any applied forces? And the answer is no. So we can say the work done by external forces equals 0. Are there any non-conservative internal forces, namely friction, doing work? And the answer is yes. We're actually calculating the coefficient of friction. So we do have work done by a non-conservative force, and it's going to be equal to the force of friction times the displacement, or the magnitude of the displacement technically, times cosine of the angle between this force and this displacement. The force of friction itself can be calculated this way. On a slope, and I'm not going to derive this now, hopefully you know this, on a slope the force of friction is mu, the coefficient, that's what we're actually solving for, times the normal force. And the normal force is mg cosine of our angle. This is the angle of the slope. This other angle is the angle between that force vector and that displacement vector. Now that we've listed all our variables, we're going to use our master equation and calculate mu, the coefficient of friction. So we start in the same place every time with this long equation. And we see that some of these terms are 0. For example, this one. Our initial height is 0, so we have no potential energy. at the beginning. Our final speed is 0, so we have no kinetic energy at the end. So we end up with initial kinetic plus the work done by friction equals the final potential. Hopefully you remember how to calculate kinetic energy. It's 1/2 mass times speed squared. So we now substitute in that expression for K, 1/2 mass times speed squared, and I'm going to put an I on the V to represent an initial speed, plus the work done by friction. That is this expression for the force of friction times d cosine theta. So it is mu mg cosine times d cosine theta equals our gravitational potential at the end. That's going to be mgh final. At this point it's algebra. It's algebra and it's plugging in. Ultimately we're solving for that variable. We can clean it up a little bit by dividing every term by m, the mass. The mass cancels out of the equation. We don't actually need to know it. I suppose that's good because we're not told the mass. I'm also going to multiply through, maybe I won't. So let's go ahead and get rid of the mass. And now rearrange and solve for mu. I suppose at this point we should go ahead and plug in for HF. You could have done that earlier in the calculation. Okay, and now we actually plug in values. So g is the acceleration due to gravity on Earth. The value is 9.8 meters per second squared. D is our 18 meters. Sine of our angle, the angle is 20 degrees. Minus 1/2 times our initial speed squared. All over g times d times cosine of our angle, that's cosine of 20, times cosine of our other angle, theta. That angle is the angle between the force of friction and the displacement. The angle would be 180 degrees because the displacement is uphill and the friction opposes pointing downhill. I'm pointing at something you can't see. The displacement is uphill and the friction points downhill. Okay, so that's cosine of 180 degrees, which many of you will know comes out to -1. Plug this into your calculator and you should get mu equals 0.31. Okay. For some of you, you will be through with the video. You can turn it off. For others, I will solve one more problem. A 75-kilogram student runs at 5 meters per second, grabs a 10-meter long hanging rope attached to a tree branch, swings out over a lake. He releases the rope when his velocity is 0. What is the angle when he releases the rope? So initially the rope is hanging straight down. He runs and grabs it, swings up until it's like over here, and he lets go. This is the angle that we're solving for, theta. Let's call the length of the rope r. So in this picture, that's r when the rope is straight down, and then r when the rope is displaced by a certain angle. And look, this is his change in height. So his final height is that amount. It goes that amount off the ground. His initial height is 0. Now perhaps you can see we have a right triangle here. And this side of the right triangle is r cosine theta. This r pertains to the whole thing. So what is the length of this height? It's r minus r cosine theta. Okay, again, let's write down all the information that we're given, assign it to variables, then we're going to write down our master equation and plug in. So we are given a mass. Is it going to cancel out? We shall find out. We're given an initial speed. We're given r. R is 10 meters. We're given the final velocity or final speed, which is 0. I mentioned this earlier. The initial height would be 0. The final height is right here, r minus r cosine theta. Does friction do any negative work? No. We ignore air resistance. We're not going to have to worry about any friction in this problem. So WNC, the work done by the non-conservative force friction, is 0. And is there any external force doing work? Well, we actually do have tension. We have tension in the rope. However, the tension is a centripetal force. And centripetal forces don't do work. That's because the displacement is always perpendicular. The displacement of the person, for example, the student, would be perpendicular to the direction of the force. In calculating the work done by tension, you would be multiplying by cosine of 90, you would get 0. So the work done by the external force of tension ends up calculating out to 0. Okay, we have Ki plus Ui plus WNC plus WEXT equals Kf plus Uf, our master equation. Some of these are 0. For example, our initial potential is 0. W is 0. This W is 0. Our final kinetic is 0. So it simplifies to just Ki equals Uf. That is 1/2 mvi squared equals mgh final, or we might say mg times r minus r cosine theta. We are solving for theta. Look, we can cancel out the mass. And we would get 1/2 VI squared equals, and can I go ahead and multiply through by G? Thank you. I'm trying to get this term by itself. So a little bit of algebra. We can plug in. G is 9.8 meters per second squared. R is 10 meters minus 1/2 our initial speed squared. All over, what, 98? That comes out to 0.8724, etc. Now we take the inverse cosine of this number. And if your calculator is in the right mode, you get 29.3 degrees. So that is the angle at which the person releases the rope, comes to rest, releases the rope, and falls into the lake. 29.3. To find the tension in the rope just before he is released, or rather, he releases the rope, okay, we can set up a free body diagram. This is part B. So we have the rope. Here's the end of the rope. There's some tension in the rope. There's the force of tension. Okay. There's gravity. And we're trying to find that tension. Okay. Now we need other equations. We need something else useful to help us proceed. I mean, we might be able to calculate the force of gravity right now. That's mg. Okay. But we need something else if we're to calculate tension. What we have is an equation for centripetal force, because the tension is a centripetal force. Okay. So we have this equation that says centripetal force, whatever it is equal to the mass of the thing that's moving on the circular path times its speed squared over r. Now actually the tension alone does not comprise the centripetal force. Tension is only part of the centripetal force. Gravity also plays a role. The centripetal force is the net force towards the center of the circular path, and the net force is tension minus a component of gravity. So we want that component of gravity. We can resolve the force of gravity into two components, and this component is going to be mg times cosine theta. That angle is theta. Just like that one. So the centripetal force is actually tension minus mg cosine theta. Okay, that's the net force towards the center of the circular path. That equals mv squared over r. However, what's our v? What's our speed at this moment in time when we have swung up 29.3 degrees? It's 0. So that minus that equals 0. Therefore, tension must equal mg cosine theta, which is 75 kilograms times 9.8 meters per second squared times cosine of 29.3 degrees, which comes out to 640 newtons. Okay, so that is the tension in the rope just before he releases it, or at the moment that he releases it. Okay. Alright, that's it for this video.